This is surface finish. It is the permanent physical record of the violent thermomechanical forces unleashed during material removal. Look at this split screen. On the left, we have a flawless, engineered titanium cylinder. On the right, a surface destroyed by thermal tearing and heavy galling. Industrial machining operates under a strict paradox. Optimizing one variable mechanically almost always triggers a cascading thermal degradation somewhere else in the system. To achieve absolute precision, you have to build a complete systems-level model. You must balance kinematics, tool geometry, thermal management, software strategy, and material science all at once. Relying on operator intuition or heuristic guessing fails. Without a multivariable thermomechanical model, consistently manufacturing high-performance components with precise surface integrity is impossible. Let's start with the baseline physical environment of a standard industrial turning operation, a rotating cylindrical workpiece meeting a stationary cutting tool. The foundational mechanical driver here is the feed rate. This is the velocity at which the tool advances along the workpiece, and it dictates the theoretical geometry of the cut. In this diagram, you see the direct mathematical correlation. As the feed rate vector increases, the uncut chip thickness expands proportionally. As the tool passes over the workpiece, that thicker chip leaves behind a heavily exaggerated sawtooth topology. The ridges become deeper and wider. To counteract this, engineers adjust the next variable, cutting speed. This is the rotational velocity of the workpiece itself, which operates entirely independently from the machine's linear feed geometry. But pushing the cutting speed higher introduces new mechanical loads. It rapidly accelerates wear on the tool and induces high-frequency vibrations that indirectly ruin the surface topology. You cannot simply slow down the feed rate and speed up the spindle indefinitely. Doing so bypasses the kinematic limits and pushes you straight into the next failure mode, the physical destruction of the tool's geometry. To understand that failure, we must zoom past the broad movements of the machine and look at the microscopic physical edge of the cutting tool. Tool design requires a strict engineering trade-off. You must balance the corner radius against the absolute sharpness of the cutting edge. This animation shows a perfectly sharp edge slicing smoothly through the material grid, but under stress, the tip rapidly degrades into flank wear, flattening out. This flattened wearland acts like a rigid stamp, physically transferring microscopic gouges into the newly cut surface. As that wearland expands, it dramatically increases the contact area at the cutting shear zone. This friction inevitably summons the primary enemy of surface integrity, rapid and uncontrolled thermal accumulation. Just look at a standard high-speed milling operation. The extreme friction at the tool workpiece interface generates intense, visible heat. Unmanaged thermal loads lead to catastrophic physical failures. The workpiece undergoes thermal softening, and molten material fuses to the tool, forming what engineers call a built-up edge. This thermal heat map illustrates an intervention. A targeted mist of minimum quantity lubrication, or MQL, enters the shear zone, causing the bright red heat pool at the tooltip to shrink and cool. When machining superalloys, MQL isn't enough. The environment requires extreme thermal management, like cryogenic machining. Watch as a directed blast of liquid CO2 hits the shear zone, turning the heat map deep blue and creating a clean boundary that prevents the chip from welding. Advanced coolants freeze the material's surface integrity in place before any thermal damage can ruin it. Now, let's look at a top-down view of a milling cutter navigating a complex internal pocket. We can mitigate thermal and mechanical loads strictly through software. Standard linear toolpaths have a primary flaw. As the tool moves into corners, the engagement angle changes inconsistently, causing massive spikes in the cutting force. The solution is a software-driven kinematic strategy known as adaptive trochoidal milling. In this diagram, the tool moves in a looping trochoidal path. The force gauge remains perfectly steady because the engagement angle is strictly constant. As the tool completes the loop, these steady forces eliminate deflection, leaving behind a perfectly smooth wall without jagged burrs. Software optimization extends hardware limits, guaranteeing surface consistency without extreme cooling or frequent tool changes. We have analyzed kinematics, geometry, coolants, and software. But look at these raw industrial billets of steel, titanium, and composites. The workpiece's specific microstructure dictates the physical response, superseding all general kinematic rules. Compare standard steel to a precipitation-hardened alloy. Counterintuitively, the hardened states actually yield smoother surfaces. This happens because harder microstructures shear cleanly under the tool's edge, whereas softer materials undergo messy, tearing plastic deformation that degrades the finish. In this close-up video, we see titanium's exceptionally poor thermal conductivity traps the extreme heat precisely at the edge. Then there are abrasive composites, like carbon fiber reinforced polymers, or CFRP. The carbon fibers act like sandpaper against the tool, requiring highly specific clearance angles to prevent matrix smearing and the separation of layers, known as delamination. Surface finish optimization is never a universal formula. It is a highly bespoke, dynamic negotiation with the atomic reality of the material being cut. If we pull back from the microscopic shear zone, we see the immense scale of a complete, modern CNC spindle operating inside a production factory. This dynamic radar chart visualizes our complete model. Surface finish is the fragile equilibrium state of parameters, geometry, coolant, strategy, and material. The polygon shifts and rebalances as different inputs are selected. The primary boss of traditional machining logic is the dangerous assumption that these variables remain static once the spindle starts turning. In reality, tool wear and heat escalate from the first second of engagement, guaranteeing static parameters eventually fail. The frontier of manufacturing solves this. Live data streams overlay the radar chart, tracking forces and actively auto-correcting feed rates and coolant in real time. This closed-loop system continuously compensates for wear and thermal loads. It ensures that the final component of a long production run has the exact same pristine surface as the first. Achieving perfect surface integrity is no longer about finding static settings. Instead, it is about engineering an adaptive system capable of surviving the evolving thermomechanical chaos of the cut.